Breaking the wall of glaucoma. Eamonn Fahy, the University of Melbourne, Australia.
Join me for a moment and do this. What can you see? It's like a tunnel view of the world, right? Now what I want you to do is make that tunnel smaller and smaller. What you see now is the kind of vision that a patient with end-stage glaucoma has. 70 million people worldwide have glaucoma, but half of them are undiagnosed. And a major issue is our ability to detect the disease before it's too late. We can measure pressure in the eye, which is a risk factor, but only in about 50% of cases. And we can detect glaucoma clinically by looking at the back of the eye and by testing peripheral vision. But these signs can take up to 10 years to develop, and by that stage, the damage is done. They call it the silent thief of sight for good reason. Now, vision is lost in glaucoma because these things, retinal ganglion cells, die off. They're the nerve cells that make up the optic nerve, and without them, we can't transmit vision from the eye to the brain. Now, the traditional view of glaucoma is that it's a one-way street, ultimately ending in ganglion cell death. But there's emerging evidence from our lab that if we treat glaucoma patients early, we can improve visual function. And this suggests that ganglion cells at an early stage of dysfunction are in fact recoverable and do not need to die. We call them comatose ganglion cells, and they can be woken up. So the question is, how can we detect these comatose ganglion cells before it's too late? And that's where my research comes in. I measured electrical activity from individual cells using a microscopic glass electrode. That's called patch clamping. This is one of the cells I recorded from and filled with a dye at the same time. I studied over 100 mouse eyes to work out whether comatose ganglion cells had an electrical signature that we could detect. And what I discovered was that they have difficulties in generating action potentials, or the signal that carries visual information from our eye along the optic nerve into the brain. Now this blew my mind, because for the first time, we had a way to detect comatose ganglion cells. I was then able to show that these cells can wake up from their coma, regain the ability to fire signal. In other words, they can undergo a prolonged period of loss of function, but still recover at a later stage. And this likely explained at the single cell level the changes we observed in glaucoma patients following treatment. Now that we have an electrical signature for comatose ganglion cells, we're one step closer to using similar electrophysiological measures in humans to detect glaucoma earlier at a point where ganglion cells are recoverable. It's my hope that one day we won't have to tell any patient that it's too late to save their vision. So let's catch this silent thief before it's stolen any sight. Thank you.